Now let's look at how well our least squares line fit the data. Okay. Now we're going to start with ignoring the line that we estimated y hat. Suppose if you do not do any regression analysis at all. So in that case, how much is the variability in y? Okay, then the extent of variability in y is measured by its variance. So variance is you take y, subtract y bar from it, y minus y bar, square it, sum it, and divide by the degrees of freedom. But for now, let's not divide by degrees of freedom. You just take the sum of squares. So your y bar is your baseline estimate. So you will take each y value, okay, look at how much is the difference between y and y bar. So you have y minus y bar. So each point you do y minus y bar and square that and add them up. Okay, that is your baseline total variability in y, because you're not using regression, you're using just y bar. So y minus y bar squared, sum that is called the total sum of squares. Now when you bring in the regression, estimated regression line, so y hat equal to 2 plus 1.25x, now the error is gone down, okay, to only that much, y minus y hat. That's the error. If you use y hat to estimate your y, then this will be the error. If you ignore y hat and use y bar, then that would be your error. So your error is now gone down to just that. Y minus y hat is the error. So the difference, that part, is now explained by the regression. The regression has explained that variation. That variation is due to my line. So that variation is no longer present in our estimate. So this is called the, so if you take y minus y hat for each of these points, square them and sum them, then what you get is sum of squared error. And the rest, which is the distance between y hat and y bar, that is the part that is explained by the regression. If you square that and sum that, that is called sum of squares of regression. So it turns out that when you add these two sums of squares, that will be equal to the total sum of squares. So here are the form of the expressions. So SST, the total sum of squares, is y minus y bar, square that and sum that. Then you have the error, square that and sum that. That will be the sum of squares of error. And then the regression part, square that and sum that, and that's your SSR. And SST is always equal to SSR plus SSE. Okay, now let's do the computations in Excel. So now this is y minus y bar squared. So this is the reason why we needed that column. So you take y minus y bar and square that. Okay, and copy that. Okay, and put the border back. And when you sum that, that gives you the total sum of squares. So this is, let's assemble that here. So SST is that. Okay. Now to find SSE, we have to set up y hat and then subtract y minus y hat. So y hat is our estimated line. So y hat will be our intercept, okay, absolute reference that, plus slope, absolute reference that, times x. So that will give us y hat, and then we do y minus y hat, right, and then square that. So that would be our error. Okay, y minus y hat is the error, and square that. Copy that down. Let's have the same number of decimal places. Okay, put the border back and sum that here. So that would be our error. Okay. Now SSR is the difference. So SST minus SSR, SST minus SSE will give you SSR. Okay. Now with this we can compute what is a statistic for how well the line fits the data. So we take the ratio of SSR, see the error that is explained by the regression. Okay, so this is the amount of error that is explained by the regression divided by the total error that we started out with. So the regression line explained, oftentimes it's expressed as a percentage. So the regression line explained 69.4% of the total variability that was present in the data. So that's called coefficient of determination. Yeah. And Excel has a function for this too. So that is called RSQ. And once again, Y first and then X. And that will give you the coefficient of determination. So how do you interpret coefficient of determination? The regression line explains 69.4% of the total variability present in the Y data. So in other words, 69.4% of the variability in sales is explained by the regression between sales and the X variable being the local payroll. Okay, 69.4% of the variability in AAA sales is explained by the regression between sales as the dependent variable or response variable and the local payroll in $100 million as the independent variable. And it so happens that this coefficient determination R squared is related to the coefficient of correlation. So remember, coefficient of correlation R is a number between -1 and +1. The sign minus or plus represents the relationship between the nature of the relationship between X and Y, whether it is positive or negative. And the number itself, the magnitude, refers to how strong the relationship between X and Y is. Okay, closer to the 1 or -1, the relationship is very strong. So if you have a +1, then that is very absolute relationship. Closer to 1, very strong positive relationship. Closer to -1 is very strong negative relationship. For example, price and demand. So if the price and demand has a very strong relationship, it will be a negative value. Correlation will be negative something. Okay, advertising expense and demand. Okay, that's likely to be positive. So you'll have, and if it is a very strong relationship, it will be a number close to positive one. Okay, number close to 0 means there is not much of a correlation going on. So from R squared to get to correlation coefficient, so we have to first find what is the sign, what is the nature of relationship. Is it positive relationship or negative? That comes from the slope. Okay, so here there is slope. Okay, so we can use the Excel function sign. So this will give you +1 if the number is positive. It will give you -1 if the number is negative. Okay, we want that here. Okay. And then R is that sign times square root of the R squared value. So that will give you the correlation coefficient. And of course, Excel has a correlation function as well, so which is CORREL. And here it doesn't matter in which order X and Y should be given, because correlation correlation between X and Y is the same as correlation between Y and X. But that's not the case in terms of what is the slope and the regression coefficients that depends on what variable is x and what variable is y. Now that will give you the correlation. Obviously that's the same value as what we got.